wanted to prove them wrong by accepting a challenge. And the challenge is that the n people gave m pieces of information, which are in the form of either this or this. So the information contains 4 integers, t, u, v, and c. And these are 2 type of informations. If t equals to 1, which means that youth person is older than the with person by at least 3 years. And if t equals to 2, that will mean the youth person is not older than the with person by at least 3 years, which is just negation of this. And you're given several informations of this similar type. And you're also given that all the ages of these n persons are integers, which can also be negative integers. And the age of the person 1 is 0. So if we denote age of the person x by e of x, which is age of person x, then you're given that e of 1 equals to 0. And now our goal is to find the age of all the n persons. But the age of all the persons should be uniquely determined. So if you are able to find the unique age for each of the person, then we just need to return yes. And if there is a case that the ith person can have age 50, 52, like multiple ages, it is not unique. Or we are not able to determine the age of ith person, any of the person, then we just need to return no. So if you see whether it is even possible to determine the ages of all n person uniquely using the information here. So if it is possible, then we just need to output yes, otherwise we need to output no. So for example, we are also given t test cases, and for each test case there will be m number of queries, and each query, as we have seen, will be in the form of t, u, v, and c. So using these m queries, we'll need to determine the ages of all the n persons. So this is just the information of the question. Now we will need to, once you get the information and you understand the whole problem, you will need to analyze it by like taking some examples, and then you will get to know which data structures you need to use and which algorithms you need to apply. So first of all, the problem statement is clear, right? Is there any doubt regarding the problem statement, or anybody didn't understand it, and should I go through the problem again? It's clear, right? So okay, so let's try to build up some intuition. So as it mentioned, there will be 2 types of informations. One is t equals to 1 and another is t equals to 2. So if t equals to 1, it says that the age of youth person, the person u is old, at least 3 years older than the person v. That means if you denote the age of youth person by EU, then EU is greater than or equals to EV plus C. So age of youth person is at least greater than 3 years by the age of youth person. And if t equals to 2, that means just negation of this inequality. So age of youth person is not at least greater than the age of youth person. So it will be EU is less than EV plus C. And since all the ages are integers, so if you want to convert this less than sign to less than or equal to, we can just write C minus 1 instead of C. So this this less than sign, we can write it as less than or equals to. So there will be like these 2 type of inequalities. We can represent each information by either this inequality or this inequality. And this C minus 1 is also just some constant C prime. Okay. So we'll be dealing with these 2 types of inequalities. Now let's consider each of them separately. So let's now first see the second type of inequality, where it says age of U is less than or equals to age of V plus C prime. Here I just replaced C minus 1, this C minus 1 with C prime, because it is at last just some integer. So C prime is also some integer which is 1 less than some C. And as you can see, this EV plus C prime, it denotes the upper bound of EU as EU is less than or equals to EV plus C prime. The upper bound means the maximum value that E of U can attain. So since the inequality says EU is less than or equals to this value, the maximum value that you can give to age of U is this. So this is upper bound for EU, right? So this is one inequality. And there are m pieces of information, so you will get multiple types of multiple inequalities of this same form. And let's say you can also combine those information. Let's say one inequality is EU is less than or equal to EV plus C1. There will be similar inequality for UV also. So EV is less than or equal to EW plus some constant C2. And if you combine both of them, then you will get another upper bound for E of U. So you just replace this EV with its maximum value, which is EW plus C2. So you can rewrite EU as EU is less than or equals to EW plus C1 plus C2. Because this is new upper bound for E of U, right? So we have written this upper bound, but we don't know the exact value of upper bound, right? Because we don't know what is the age of the Vth person, what is the age of Wth person. We don't know this value yet. So we don't know the exact upper bound for EU, right? Because that is the question. We need to determine the ages of all these persons. So for determine the upper bound also, we will need this age here, this value, right? But all the informations. So if you consider all the informations, we will have some at some point we will get this type of inequality where E1 is also involved in the equation. So once E1 gets involved in the equation, we know that we are told E1 equals to 0. The age of first person is given 0. Then we can replace each of these values sequentially in its next equation, and we can get a constant upper bound. So consider this example. So we are given EV1 is less than or equals to E1 plus C1. EV2 is less than or equals to EV1 plus C2. And similarly, EV3 is less than or equal to EV2 plus C3. And there are k such inequalities. EVK is less than or equal to EVK minus 1 CK. So if you put this upper bound of EV1 here, so it will become EV2 is less than or equals to E1 plus C1 plus C2, right? Then you can put this value here. So it will become EV3 is less than or equals to E1 plus C1 plus C2 plus C3. At the end, you will get this equation. EVK is less than or equal to E1 plus C1 C2 up to CK, and you can replace E1 with 0 as it is given in the question, and you will get a constant upper bound for EVK. So now we know what is the value of this upper bound, right? Because we know what is the value of C1, C2, and CK. Here, we didn't know what is the value of EW or EV. So that's why we were not able to determine the upper bound exactly. Now, if you combine all of these equations, you are able to determine the upper bound on EVK exactly. But this is one way to solve these equations. There can be another set of equations which can give some other upper bound on EVK, right? So now we need to keep track of these equations and inequalities and this upper bound. So that's before that we will need some type of data. So if you think by taking some observations, you will get some intuition that if we represent, say there is inequality, EU is less than or equals to EV plus C. If we represent it in terms of vertices and edges, like graphs, so U is a vertex, V is a vertex, and if we put an edge from U to V, which has a weight C, right? So now, if if we represent this inequality, and just a minute, see, let me just we want EV to be here and EV plus C to be here. So if you see, we want to traverse from this vertex to this vertex intuitively, right? So if we put a vertex in this direction, and if we traverse from vertex V to vertex U, so this will, what intuitively this tells is, if we know the upper bound on EV, and if we go from V to vertex U through this edge, which has a weight C, then we will get an upper bound on U also, which will be EV plus C, which is same as the cost of traversing, right? So if you traverse from this path, it will be EV plus C. And if there is some other inequality, EV is less than or equals to EW plus C2, you can put it here. This is for vertex W, and it has weight EW. This is the vertex, and I'm giving a weight to the vertex, which is EW, and this edge has weight similar to this inequality. So now if you traverse from this W to U, so what is the cost of traversing? So assume you have initial cost EW. This H will add a cost of C2. This H will add a cost of C. And if you observe, this is the same as the resultant inequality by combining this and these equations, which is C plus C2 plus EW, right? So this gives us the intuition that if we represent this inequality in terms of graph, we will be able to get some result, right? Now let's try to represent this set of inequalities in terms of the graph. So if we consider each equation one by one, so there will be one vertex with vertex 1. For the first equation, there will be edge from 1 to V1 with weight C1. So there will be edge from 1 to V1 with weight C1. From the second equation, there will be edge from V1 to V2 with weight C2. For the third equation, there will be edge from V2 to V3 with weight C3. And if you continue this process, at last there will be a vertex Vk minus 1, which will be connected to Vk with HCk. So this is the last inequality. And now, from this path, what you will get is, since the age of a person 1 is 0, we can assume that initial cost is 0. And if we traverse from vertex 1 to vertex Vk, so cost of traversing from vertex 1 to vertex Vk, so the cost will be C1 plus C2 plus C3 up to Ck, right? So the traversal cost gives the upper bound of vertex Vk. So we started from vertex 1, we went till vertex Vk, and the cost gives us the upper bound for the edge of Vk. Similarly, if you only traverse through V1, so this will give us the upper bound for V1. If you traverse till only V2, this will give upper bound for V2, C1 plus C2. If you traverse only till V3, this will give us upper bound for V3, which is C1 plus C2 plus C3, right? And there may be some other path from vertex V1 to say Vk plus 1, Vk plus 2, and then it is going to Vk. So it is not a unique path. There can be other paths also, which will give some, if you traverse through that path, this will give some other upper bound on the edge of Vk, right? So consider you find all the paths from vertex 1 to vertex Vk. Some path, say first one path has cost 3, one has 5, one has 6, and one has 7. So what this cost represents? It represents the age of Vk is less than or equals to 7 for this path. Age of Vk is less than or equals to 6 for this path. Age of Vk is less than or equals to 5 for this path. And age of Vk is less than or equals to 3 for this path. So for all paths, we will find the cost and we'll get these inequalities. And now, out of these four, which should I consider such that all of them get satisfied? So if you see these values, I want to select only one of these such that all of them should get satisfied. So if I select this value, this particular value, EVK is less than or equals to 7. So it then if we choose EVK equals to say 4, then it will not satisfy this inequality, right? So which of these should I choose such that all of them get satisfied? So if you choose this minimum value, the inequality which has the minimum value, then all the outputs which this will give will satisfy the upper three inequalities also, right? We say VVK is less than or equals to 3. We are already saying that this is less than or equals to 5, less than or equals to 6, and it is less than or equals to 7. So you just need to consider the inequality which has the minimum right side value. So now, in terms of graph, what does this inequality suggest? Can someone say, like, here we can say that we need to choose an inequality which has the lowest value on the right side. And this values represents the cost of traversing. So which path should I choose to get this inequality? So since here we choose the minimum value inequality, here also we need to choose minimum value, this minimum value path, which is the shortest path. So if you choose the shortest path from vertex 1 to vertex VK, it will give the tightest upper bound on the edge of person VK, right? So if you build the graph this way, then you just need to find the shortest path from vertex 1 to V1. It will give the upper bound for vertex V1. If you find the shortest path from vertex 1 to vertex V2, it will give the upper bound for vertex V2. And similarly, the shortest path from vertex 1 to vertex Vn will give the tightest upper bound for the vertex Vn, right? This is the one type of graph that we have built for this type of inequalities. All the inequalities which are in the form of this. So we got this is less than or equals to. So by combining all these type of inequalities, we built up a graph. Then we took the first vertex 1 and we find the shortest path from 1 to all of the vertices, and those cost give me the tightest upper bound for all of those vertices, right? Now, this is we talk about this type of inequalities. There are this type of inequalities also, which is type 1. EU is greater than or equals to EV plus C. So let's see what will we do in this type of inequalities. EU is greater than or equals to EV plus C. Right. So here, if you like here also we want to make another graph to get this upper bound. So here it's lower bound. So if you see, this inequality says the value of EU is always greater than this value. So it gives me lower bound of edge of U. Here we can also consider similar cases that we did in the case of upper bound. So if there are two inequalities, EU is greater than EV plus C, EV is greater than or equals to EW plus C1, you can combine and get EU is greater than or equals to EW plus C1 plus C2. So if we have a series of inequalities, E1 is greater than or equals to E1 plus C1, EV2 is greater than or equals to EV1 plus C2, and EVK is greater than or equals to EVK minus 1 plus CK. You can combine all of them and the resultant inequality will be EVK is greater than or equals to E1 plus C1 plus C2 up to Ck, and you can put E1 equals to 0, so it will become C1 plus C2 up to Ck. So through this, you'll get the tightest lower bound for this vertex. Earlier, we got the tightest upper bound. In this case, we'll get the tightest lower bound. So if we want to represent it in terms of graph, so EU is greater than or equals to EV plus C. So we'll take vertex U, we'll take vertex V, and the lower bound on V is say EV, and we put a H from U to V with weight C. So now if you traverse from vertex V to vertex U through this path, it will tell me that since the lowest bound of vertex V is EV, the lowest bound of vertex U will be EV plus C. This C is the cost of traversing from V to U. So now if you want to combine all of these inequalities in terms of graph, this type of graphs, so we'll get there is vertex 1 which has H from vertex V1 which has weight C1. There is vertex 2 which has H from V2 to V1 with weight C2, and which will go to vertex Vk which has weight Ck. Right. So here also I want to find a path from 1 to Vk, but since these edges are in different direction, I will if I negate these weights, let's say I flip these inequalities. Let's say we write this inequality in this way: E V1 is greater than or equals to E1 minus C1. So I just want to find a path from vertex C1 to Vk, which give me lower bound or the edge of Vk, right? But if I go through this way, I won't be able to find a path from V1 to Vk, since these edges are directed towards the vertex 1, not towards the vertex Vk. So I will just reform the equations in this form. So I will take the C1 in the second side, in the another side, so it will become negative, and I can rewrite the equations in this form. So EV2 will be greater than or equals to EV1 minus C2, and at last there will be EVK, which will be greater than or equals to EVK minus 1 minus Ck. And now if I add H from 1 to V1 with weight minus C1, V1 to V2 with weight minus C2, and at last there will be weight from Vk minus 1 to Vk with weight minus Ck. So if now I traverse from vertex 1 to Vk, you can observe that the cost is minus C1 minus C2 up to minus Vk. And this is the lower bound on the edge of vertex Vk, right? And suppose you are given several lower bounds on Vk. Say EVK is greater than or equals to 2, EVK is greater than or equals to 3, E is greater than or equals to 5. To satisfy all of these three inequalities, which one will you choose? So I want to choose only one of them such that all three get satisfied. So earlier in the case of less than or equals to, we chose the value which was minimum. Now it is just different, like it is just opposite. We want to choose one equation where this greater than or equals to inequality gets satisfied. In this case, instead of minimum, we'll need to choose the maximum right hand side value, right? Because if we consider this EVK is greater than or equals to 5, it already satisfies greater than or equals to 2, 3, and greater than or equals to 2. So here we need to choose the inequality which has the maximum right hand side value, and that will give me the tightest lower bound of EVK. So to get this maximum value, now earlier we saw that we need to, for the minimum, we need to choose the shortest path. But now since we want to get the maximum value, we need to choose the longest path from vertex 1 to vertex vk, right? And that longest path will give me the tightest lower bound on the edge of vk. But we don't have an, like in the lectures, we haven't studied any algorithm for longest path, right? We only studied algorithm for finding the shortest paths, Jasper algorithm and Bellman-Ford algorithm, right? So we want to convert this longest path problem to shortest path because we already have algorithm to find the shortest path. So what we can do is uh, consider this example. There are 4 vertices. This vertex, this edge is 3, 4. This is 2. This is 3. So here, what will be the longest path from vertex 1 to vertex 4? So if you go from this path, it will have weight 5. If you go from this path, it will have weight 7. So this is the longest path, longest cost path from 1 to 4, right? Now if I just negate all the edge weights, say -3, -4, -2, and -3, and now if I find the shortest path from vertex 1 to vertex 4, it will be same as the longest path that we got when it was positive values, right? So if you consider this path only, it will result in weight -7, and this will result in weight -5. So -7 is the smallest bit among two. So if we now find the shortest path in this graph, it will give me the tightest upper bound on the vertex 4. So just to convert this longest path problem to shortest path problem, we will negate all the edge weights. So if there is weight 5, we will put -5. If there is weight -6, we will put 6. So you just need to negate all the edge weights and the problem will become the shortest path problem. So till now we have built 2 types of graph, out of in which both type of graphs we want to find the shortest path from vertex 1 to all other vertices. And this first graph will give me the upper bound on the edges of those vertices, and this second graph will give me the lower bound on the edge of all of those vertices, right? So consider we have built both of the graphs, we have find the shortest path in both of the graphs, and at last from the first graph we got EV1 is less than or equals to this U1, EV2 is less than or equals to U2, up to EVK is less than or equals to UK. So these are upper bounds of all the vertices, and through path 2, we got EV1 greater than or equals to L1, EV2 greater than or equals to L2, up to EVK greater than or equals to LK. So by doing the shortest path algorithm, we will get these values, right? Now we have upper bounds and lower bounds. So to find the final answer, we just need to compare these bounds. So for EV1, if say L1 equals to U1, then we can say that EV1 will be always equal to L1, will be equal to U1. So we are able to uniquely determine the age of person V1. So for the case of person V1, we are sure that we will be able to, his age is L1. Let's say for V2, L1 is less than U1. So in this case, EV2 can be L1, L1 plus 1, L1 plus 2, up to U1, U2, right? I just put 2 to just to differ it from EV1. So if this is less than, L2 is less than U2, we are able to give multiple values to EV2. So we are not able to uniquely determine the value of age of V2 person, right? So this contradicts the given condition in the question that we should be able to uniquely determine the age of all the person. So since we are not able to uniquely determine the age of V2 person, in this, if there is some vertex for which this happens, we'll just output no. And for the third case also, if L2 is greater than U2, we there is no value that we can assign. There is no real value that we can assign to v2, right? Because it says that ev2 is greater than or equals to 3 and ev2 is less than or equals to 2. So there isn't any value that we can assign to v2 that satisfy this both of these inequalities. So if this type of inequality, this type of case comes, we will also output no. So after getting all the lower bounds and upper bounds, we'll check each of these values, and all of these values are of this form, then only we will output yes. If any of the value are in the form of these two inequalities, either lower bound is less than upper bound or lower bound is strictly greater than upper bound, then we will output no. Only if lower bound is exactly equal to upper bound for all the person, we will output yes, because then only we will be able to uniquely determine the age of all the persons, right? So this was the whole idea for solving this question. The thing is, to use the shortest path algorithm, you shouldn't use the Dijkstra algorithm. Why? Because in the question, it is given that all the ages are integers, strangely not necessarily positive integers. So it can be the case that the age of the graph is negative. And we are also negating the values in this first lower bound type of inequalities, right? So if some age is positive, we will make it negative. So the Dijkstra algorithm we can only use for positive weight ages. Since we have negative weight wages, to find the shortest path, we'll need to use Bell-Manford algorithm. So this was the overall idea how to solve this problem. And I will just go through the code part, how we can implement this algorithm, like how we can implement the code to solve this problem. Just a second. So what I have done is, first I have taken the test case as input, then N and M as input. I have created two graphs. This is array of graphs G0 and G1. In the first graph, I will, in the one graph, I will store the lower bounds. In another graph, I will store the upper bounds. So in this loop, I have just I have just added edges to this graph. So I have taken this T, U, V, and C as input. And in this is for t equals to 0, this is for t equals to 1. In both of the cases we'll get some inequality, right? So and for one equality we will get two bounds. So since say the inequality is between u and v, if the inequality gives lower bound on u, it will also give upper bound on v, right? So for one information I will need to add each to both of the graphs, one for lower bound for u and other for upper bound for v. So this for the lower bound I will add it to the G0, and for the upper bound I will add it to the G1. And here for the case 2, for the case where we want to find the we want to negate the edges, I have it was this case 1 where we want to negate the edges to convert the longest path problem to shortest path. So we have negated the C to minus C, so that we need to just find the shortest path in that case also. This swapping is just to manipulate some of the edge, like it is just to make this code smaller. So you can remove this swap, and then you will need to add some conditions, like you need if whether you want to add edge from u to v or v to v, that you need to specify here. So this swapping just make it easy. Like if I want to add an edge from u to v, I just swap the v to u and I will add edge from v to u. So that will give me the same edge. So this you can ignore and manually put that condition here also. This is for adding the edges. Now I will apply the Bell-Manford algorithm on both of the graphs. So what Bell-Manford algorithm does is it initializes the distance array. This distance array is the distance, the ith element of this distance array denotes the shortest path from the vertex 1 to vertex I. So I will initialize the distance of 0 with 0th vertex with 0, and I will run this outer loop for n-1 times and the inner loop for n times, and I'll see if the parent vertex has has some finite distance, and the child vertex, the parent vertex plus its the edge weight is lower than the current value of child, then I will update that weight. So after running this algorithm for n minus 1 times, I will run it for separately for one time to see if there is still some edge for which some vertex for which I can update this path, which denotes that there exists a negative cycle. Right? If you seen the lectures, so after this n minus 1 iteration, if we still run the algorithm and we can get the better path length, more improved path length, then there exists a negative cycle. So I just put a global variable negative cycle and I updated it as 1. So if I found there is a negative cycle, I'll just return no, because that case I will not be able to determine the age of that person, right? And only both of the arrays are equal, all the elements are equal, then I'll output yes. Otherwise, I will output no. So this was the whole algorithm for this whole implemented part of the idea that we just went through. Yeah, I think there will be participants on YouTube only. So
yeah, I'm just checking the YouTube stream. As of now, I don't think there are any questions about your explanation so far, but I think yeah, on Discord, I think I've just shared the link to the question. I'm not sure if maybe you can just share the link to your code with me, or you can just share it on Discord directly for
yes.
This code is actually very clean, and I think should be extremely understandable after people have followed your sort of the explanation from before. Of course, for anybody who's watching this later, I definitely recommend trying to code it yourself first. But on the other hand, this is sort of a good reference for people to have. Yeah.
Yes, I'll share it on Discord.
Yeah, you can share it later on Discord. That should be great. All right, Gaurav, I think that was a really nice problem and really cool application of negative cycles. So yeah, thanks so much for going over it in all this sort of detail and depth. So very nice. Thank you. And Nipun, do you want to take it from here and talk about the badges problem?
Sure, ma'am. Just want to make sure I'm audible.
Yeah, you're audible. I'm not sure. Are you sharing your screen yet or you're about to?
No, I'm just going to share my screen.
Okay, sure.
It's my screen, isn't it?
It says you've started, but I don't see it yet. So maybe just 1 minute more, I guess.
I think it should be visible now.
Visible now, yes, yes.
That's perfect. So, hi everyone. I'll be discussing week 8 problem assignment, which was based on flows. And the problem is as follows. A badge is created by superimposing two squares, and the bottom square should be of blue color and the top square should be of yellow color. So they're given a bunch of squares of two colors only, yellow color and blue color, and they are rotated in such a way that once superimposed, the whole figure will have 8 vertices and distinguishable vertices. So there was a reference image attached with this link here, but I'll just tell you what the figure should look like. The first square is something like this, and the second yellow square, once rotated, and that should be on the top of the blue square, and it should be something like this. So it has 8 distinguishable vertices. So this 1, 2, 3, 4, 5, 6, 7, 8. But if you have a situation where you have some squares like um, this is not allowed. I mean, this has just four distinguishable vertices, 1, 2, 3, right? If you want this situation is allowed, this situation is not allowed. And then you say that you are given n squares and each of a given color and the side length. So you know the side length of these two squares, um, you know, and determine the maximum number of badges that you can make. So one of the cases is that you want to superimpose one patch on the other, and you have a universe of squares where some are blue and some are yellow, and then you want, and there is another condition that you can know that each square can be used for at most one badge. So you want to make sure that once you have used a square, either blue or yellow, you cannot use it again. Uh, so essentially, it is difficult to visualize this problem maybe as flows, but what you can think about in terms of graph is you have a graph. If you try to model this as badges, you have two colors of badges. So this basically tries to boil down this problem to a bipartite graph. It has two sections, colored blue or yellow, right? And so what I'm proposing is that you can divide your whole set of badges. One would be of yellow color badges, and would be of blue color badges. Blue color badge, right? And just so you have some yellow color yellow color squares here, and some blue color squares here. Now the vertices are set, and now so for example, I don't know, you have n and you have uh, probability. So and then you said, how do you know that there is an edge between a yellow vertex and a blue color vertex? See, I'll say that you have an edge between from one of the vertex to the other. Once you know that this is I can make a pair out of these vertices, and it is mentioned in the question that only a blue and a yellow square can make a badge. So there is not any point in having edges between these vertices. There is no point having edges like these, because an edge, by definition that I'm proposing, denotes that the two vertices at the end of the edge can make a badge, and two yellow vertices or two blue vertices cannot make a badge. So that's why I was saying that it is a kind of something like a bipartite problem. And if you want to have an edge between a yellow vertex and a blue vertex, then they should make a badge, and you have to work out what are the cases in which there should be an edge. Okay, so let's see. And so essentially, if you don't think about any condition other than the color, then this should be a complete graph. So you can match this. You can have I'll just switch my color. You can have this edge, this edge, this edge. So basically, M into the edges you can have, and similarly for all these edges. So the thing is, all these edges cannot make all possible badges because of the condition here that once superimpose, there should be 8 distinguishable vertices. So this is a bit of geometry that how do you make sure that once you superimpose two squares, then you get 8 distinguishable vertices. So consider an example here. So let's take an example, and in this example, I'll just take. So the blue is the bottom. So the blue is the bottom, and yellow is on top, right? So the yellow is just under the blue, like the yellow is circumscribed by the blue square, and for notation purposes, the edge length of the blue square is SB, and the edge length of the yellow square is SY. And you can see that if SY is just, so if I change my value of SY to SY dash, with SY dash greater than SY, you can see that it will just go out of the blue square, and the next situation will be something like this. So you'll have 8 distinguishable vertices instead of 4, right? So currently what happens is the following. So take the center of both the squares, and I'll suppose that the center of one square is over the center of the other square. It is overlapping, and this is HP by 2, and then you have this length, and this is 90 degrees. And because this has 45 degrees, this is 45 degrees, this is 90 degrees, and then this length is HP by 2. Right, and you can say that, yeah, and this length will be HP root 2, but for the notation purposes, I'll take it as, I'll just move it. Take one here. 90 degrees, and this is SP by 2, and this is HY. Right. So currently you have the relation that SY by 2 square by Pythagoras theorem square is equal to SB by 2 square, and HY square by 2 is equal to HP square by 4, or HP square is equal to HP square by 2. SY is equal to SP by root 2. Okay. And if I have a condition where SY is greater than HP by root 2, then you can see that the yellow square will just go out of the blue square. So this condition is favorable. But the thing is, it may happen that once you keep on scaling the yellow square, there's another condition that can occur, which is very likely to occur, is you have the blue square as that, and you keep on scaling and scaling, and this condition occurs. That yellow may grow as much blue was, maybe twice the blue or some by factor of k, length of blue, and it may basically hide blue, right? So you don't want this condition to occur, and for that, by working out the same geometry, or intuitively you can just flip SY and SP, and in the condition that SY should be smaller, or SP should be smaller than SY by root 2, or SY should be SP should be smaller than SY by root 2, and this should be great, right? Yeah, this should be great. This by flipping SY, and SY should be smaller than 2 SP. So this is condition 1, and this is condition 2. So just going back to this graph problem. So for every pair of vertices that satisfy this condition, this pair or this pair or this pair or this pair, you just keep that edge. You don't, if this edge, if this length, if this is HB and this is HY, if this pair does not satisfy these two conditions, so there is an AND between these two conditions. These two should be satisfied simultaneously for every pair of blue and yellow squares. Then you did that edge. So this edge was not there. And simultaneously. So you get a bipartite graph at the end of the whole algorithm. You get a bipartite graph. So with 2 and with yellow, and with some pair of edges, between them. We don't know how many edges yet. And so the next thing is you have to take one blue, you have to choose an edge, And the endpoints of this edge, one would be in blue, one would be yellow by the definition of bipartite graph, and that should form a badge. And you can never choose an edge like, okay, I will choose this edge and I will choose this edge. No, this is not possible, because every square can be in at most one badge. So if you use these two edges, that means you are proposing that I will use this square twice, which is not allowed. Okay. So okay, you have a bipartite graph now, and now the only thing left is have to have a matching between the yellow squares and the blue squares. And for matching, there is a very nice algorithm that you can use for max flows. So basically, just construct another S vertex and join these with all the blue vertices, and here also there's a sync vertex, and you pass where edge capacities can be 1, and also that its capacities are 1, and also its capacity is 1. So S to Bi, this is the mode, this is R1, Pi to the vertices are also 1, and yellow vertices to sync is also 1. Right? So this is your whole model of the graph, and once you push maximum flow, and you can probably use algorithms to calculate the maximum flow, maybe float propulsion algorithm, then you can get the maximum matching out of this bipartite graph. And once you get the maximum matching, that means you can construct that many number of badges, and no vertex will be counted twice in any edge by the definition of matching. So you will get the maximum number of badges. That's the whole idea. The graph.
Yeah, I think that's perfect. Yeah. So basically for these max flow kind of problems, the crucial thing is really being able to come up with the graph model like you just described. Because after that, at least from an implementation point of view in a contest, you can just, after you construct the graph, you can just invoke max flow and basically just return the output. That's it. Again, if you look at the lectures, you'll find descriptions of max flow algorithms. And if you look at the repository, you'll find the code for some of the standard max flow algorithms. So that's kind of available, and you don't have to worry about that aspect of it so much. It's really about building an appropriate graph and sort of appreciating that the flow corresponds to the solution for your construction. So here the crux of the matter was to understand that an edge should be present. First of all, that you need vertices corresponding to the squares that have been given, and that the edge is present only when the two squares can form a compatible batch. So there was a bit of a geometry calculation there that needed to be worked out so that you could come up with that condition. So whenever that condition is satisfied, you have these two conditions. When they're simultaneously satisfied, like Nipun explained, that's when you put that edge. So yeah, I think that this kind of covers it. And once again, I don't see any questions related to this problem on the YouTube stream, but I do see that a few people are tuned in. So I hope that, this explanation was clear. I think the week 9 programming assignment the deadline for that has also concluded yesterday, but we won't have time on today's stream to discuss that. So we'll pick that up next time. And the DP assignments we will discuss the week after, like basically in the last live stream is when we will discuss the DP based assignments, because that's kind of the last programming assignment that you have. So weeks 11 and 12 don't have programming assignments in them. So there's just one DP based assignment, and we will discuss that. So we'll discuss week 9 next week and week 10 the week after that. So that's kind of the plan at this point. So thanks, Nipun, for that excellent explanation. And since we don't have we don't have anyone joining on Zoom at the moment, I think there are no questions to be taken from here. So I guess we can call it a wrap. Yeah. All right. So yeah, thanks very much to both Gaurav and Nipun. And I think Mr. Karthik, we can conclude the live stream and close the Zoom session as well. So Gaurav and Nipun, if you want to leave, that's fine. I'll just be here till the session is closed. Yeah.
Sure, ma'am. Thank you.
All right. Thanks.
Sure, ma'am. Thank you.
Yeah. Thanks a ton. Good night. Bye.